Hello, good morning. Hi. Hopefully you're here for Intro to Hacking with the Raspberry Pi. But first, I kind of want to show of hands, at least from this room. I can't see the other theaters, but who's heard of the Raspberry Pi? Hopefully, yeah, pretty much everybody. Good. Okay. Who owns at least one? 3/4 of you, maybe? That's cool. How many of you own one, but it's sitting in a junk drawer or a closet or in a box somewhere? Or a good chunk of you. Yeah, that's kind of about what I was expecting. And how many of you are slightly daunted at the idea of tinkering with electronics or hardware things? Some hands. All right, cool. So this talk is probably for you. And then I want to say, if you already understand things like some circuitry basics, are familiar with breadboards and wiring, know how to program the Gpio on a Raspberry Pi, this talk may not be for you. So, if you needed to leave now, I wouldn't be offended, really. So good morning. Glad you all could wake up so early for this. My name is Sarah Withee. I like to call myself a friendly polyglot software engineer, so I tend not to stick with any particular language. I really like working with a wide variety of things. In some form or another, I've been a hardware tinkerer, a robot builder, and now I tend to be more and more known as somebody who has an artificial pancreas, which you can find me in the hallway and ask me about later. I'm also on Twitter at Geeky Girl Sarah. And if you don't recognize this woman, her name's Simone Yates. She's kind of known on YouTube as the shitty robot builder. But she held a workshop in San Francisco once, and I got the opportunity to meet her, as well as build a really terrible robot, which is Bruce, who's made from popsicle sticks, some servo motors, and has a grape for a head. So a little bit about today's talk. I'm going to start a little bit talking about the Raspberry Pi, a little bit about the technical specs of it. We're going to dive into some of the hardware, different things we can tinker with that, learn about circuits and how they work with the Raspberry Pi. Go into the programming aspect of it, which I think is the daunting part, even though it ends up being really simple. Show off a few sample projects, show maybe some future inspiration for things you could build with this, and then kind of wrap it all up. So to kind of get a basics for what the Raspberry Pi was originally designed to do, they call it, from their website, they say it's a credit card-sized computer that plugs into your TV and a keyboard. It's a capable little computer which can be used in electronics projects and for many of the things your desktop PC does, like spreadsheets, word processing, and games. It can play high-definition video, and we want to see it being used by kids all over the world to learn programming. And I think this is a great ambition, but of course, all the adult nerds said, hey, that thing's cool, I should buy a bunch. So, and then I think, kind of like me, I ended up buying one and just kind of like, well, what do I do with it now? And, but I also like this description from hackaday.com for the word hacking. And they said, we're taking back the term hacking, which has been soured in the public mind. Hacking is an art form that uses something in a way that was not originally intended. This highly creative activity can be highly technical, simply clever, or both. Hackers bask in the glory of building it instead of buying it, repairing it rather than trashing it, and raiding their junk bins for new projects every time they can steal a few moments away. So any of you, by this definition, consider yourself maybe a hacker? 2 hands? Oh, wow. Hopefully I can inspire a few more of you to raise your hand a little later. So I'm going to go over a lot of things, and I don't expect any of you to really memorize any of this by the end. So all of these slides, all the codes, the wiring diagrams, the videos of the sample projects, everything is up on my website. So geekygirlsarah.com/Raspberry Pi, and you can see literally everything here. So first, let's dive into the Raspberry Pi. If you haven't seen it, that's this little lovely doodad here. And I'll talk a bit more about kind of what I've modified on it here in a minute. But some of the history behind it, back in 2006, they had the idea of starting to build this thing. So the idea of this is not new at all. But it wasn't really until 2008 when some of the processors became cheap enough to actually make it reasonable. By 2011 was when they finally got like alpha versions and beta versions out to people. And then they sold the first ones in 2012. And then pretty much every year after that, they made some sort of modification to it, made it a little bigger, a little better. Surprisingly kept the really same cheap price model for it. And these are the basic models. The A+ and B+ were one of the original ones. I didn't bring one of those with me, but that's the first one I ended up buying was the B+. They released the 2 like a year or 2 later, and then the 3+, which is one of the newest ones I have here, came out, what, 2 years ago, I think. The Pi Zero, which is a much smaller one, so it's designed to be kind of built into like portable electronics or things like that, so a much smaller scale. And then the Z, which is kind of like the upgraded version of the Zero. I won't go over the tech specs, but you can kind of see like as they evolved, they kind of got better and better. The one thing I will point out is the W and the WH. The W is just the flat board, and the WH is with the headers. So if you're tinkering around, that's probably the one you want, since you can plug the wires into it a lot easier. Unless you really like soldering, then you can get the W. All right. So I'm going to dive a little bit into the hardware. And to do that, I want to kind of go back to maybe your physical science classes back in like high school. So we might remember circuits, and a circuit is basically a complete route that electricity can travel through. Really simple explanation. There's 2 main kinds of circuits. The first one's series circuit. You may kind of vaguely remember this. The electricity can flow just in one direction. It's basically one loop. So in this particular little drawing up here, if you close that switch, then the electricity can flow in a single loop around it. So the light bulb would be able to turn on. When you open the switch, you do not have a closed loop. And so the electricity can't flow, and the light bulb stays off. For the parallel circuit, basically, at some point, the electricity splits off and can do multiple things. So when you close the switch in this one, electricity splits off, lights up both light bulbs, and then comes back together. You can, of course, move that switch around to different places to turn on individual lights and things like that. And basically, like everything we're going to do is basically turning on and off a whole bunch of different parallel circuits. If you've seen one of these before, it's called a breadboard. And I have one here with a bunch of different doodads on it. I know you can't probably really see it, but I'll have pictures of it in a minute. But basically, it's a prototyping system that you don't have to really solder anything together. And this is a literal breadboard, which is where the name came from. So normally a board you would cut bread on, where people would just like drill in wires and different things on it. We don't really do that as much anymore because we have these lovely things. So this is a circuit I found online. I don't know what it does, but kind of shows an example of, you just literally plug wires into the holes, and you can build all these different circuits. So how it works is generally when you buy one, it's just the board itself, but you can also buy it with kind of like an additional board attached to it. So what you would do is you wire it up on the 2 binding posts up there, or just wire like power and ground straight into the holes. And I'll cover that in a minute. But the parts I want to point out is along the top and the bottom, or depending on which side you hold it on. There's a red line and a blue line, and those mean the holes are connected all the way across the length of the board. And then in the middle, there's all these different, like, shorter rows. And those are the ones that are connected to each other in just sets of 5. So anytime you plug in 2 wires into the same set, you can build that continuous circuit. This picture is kind of the inside of a breadboard and what it looks like. So I think it kind of helps show a little better kind of what the inside looks like and what all's connected together. So if I were to build a normal regular circuit, we would use some sort of power source. In this little drawing, I have like a little battery pack. And I have a power wire, which is the red one that would go from the positive end of the battery to the red rail on the breadboard. And then you can use the blue wire in this case to go to the blue line of the breadboard to be the negative power. And the colors don't matter, but generally you want to like make some system up so you remember later. And then whatever you want to do in the middle, you just kind of connect to the power rails and kind of do whatever. So in this case, I have a little LED in the middle. But we're not using a battery pack. We can use a Raspberry Pi. So as long as the Raspberry Pi is on, it will provide a power source through the little pins up in the top. So we can take the one that's labeled 3.3 volts, and that can be our power source. And then there's a whole bunch of them labeled ground, and any of those can be sort of the return power or the negative power back. And if any of you played with Arduino, you might be familiar that it uses 5 volts. The Raspberry Pi uses 3.3. So if you have, the parts aren't necessarily interchangeable, you might have to do a little bit to get them to work back and forth. All right, are we all with me so far? Cool. All right. So GPIO is the pins up here, and it stands for General Purpose Input and Output. So basically, this is the way we can talk to anything that's connected to a Raspberry Pi. Pretty much every model except the very first one has 40 hardware pins. And the good thing is they're compatible with each other, so as they've continued to upgrade the models, all the pins have stayed the same. There's 2 3.3 power ones, 2 5-volt ones, which we won't pretty much use, 8 ground ones, 20 GPIOs, which are the ones you can manually control with code, and then 2 miscellaneous ones, which we're not really going to talk about. And unfortunately, they're not labeled. So it's just literally 40 pins, and they don't really tell you much about what they do. But I do have this chart, and it's also on the website. And it tells you literally what all of the pins do, which is really, really cool and really, really helpful. In fact, I printed it out and actually stuck it literally on top of my board. So I can like punch wires straight onto the pins and know actually what they're plugged into. So you can kind of see there's a whole bunch of different types. The colors kind of distinguish what the different types are. And the ones labeled GPIO, obviously, are GPIO. But in gray, there's kind of a extra little thing. So some of them have some special features that you can use too. And we'll talk about a couple of those a little later. All right. So that's like the really quick overview of like all the hardware stuff. So hopefully that wasn't too hard to digest. Now let's go into the programming, which is really why you're all here, right? Okay. So on the Raspberry Pi, Python is built into the operating system when you get it. And all the GPIO libraries are already downloaded and ready to use. So all you gotta do is just import them in and start programming. There's a bunch of different libraries available for different languages too. I think you actually have to go out and fetch those though, but they're all pretty easy. And I think I've seen C++, Java. I think I saw one on PHP once, which is kind of interesting. So I know there's a bunch of different languages for these. So the first thing you need to know when you're programming the Raspberry Pi is which mode you want to use. So basically, the board mode is the physical pin. So on the left side, you can see the pins are 1, 3, 5, 7, 9, and then on the right side, 2, 4, 6, 8, 10. So those would be the physical pin numbers. The BCM mode is basically the GPIO pin number. So if you looked, you can see like on the left side, there's 3.3 volts, but then GPIO 2, 3, 4, ground 17, 27, 22. They're kind of not numbered in order, but that's kind of where this mode sort of becomes important. I think it's easier just to use board, and I'm probably going to do that throughout the course of all this code. So next, all you got to do is import that library we talked about. So it's just rpi.gpio. Just import it as GPIO for a little simpler wording. And then pick which mode you want to use. So set mode, either board or BCM. Once you've done that, now you can start to use any of these pins to do whatever you want with. So you can set them as inputs or outputs. So you're either reading from the pin or you're sending a signal out through the pin. And you can change these anytime you want in your code. We'll end up doing that in one of our projects too. So all you gotta do is just pick whichever pin number and then which mode you're gonna use it for. To write out to the output pins, it's really simple. You just use the output function, the pin number, and then what value you wanna send to it. So for the Raspberry Pi, you can either turn it on or off, in which case would be 3.3 volts or 0 volts. And you can use either true or false for on and off, high and low for 3 volts or no volts. You could probably either use some sort of 1 or truthy value or 0 or falsy value. To read from any of those pins, you just read the input function with the pin passed into it. And it will either be true or false or 1 or 0, depending on how you want to process that. So also, again, pretty simple. The Arduino has some analog pins. The Raspberry Pi does not. So that's sort of outside of the scope if you want to do anything with that. And then finally, when the program ends, you should kind of clean up the input-output states of all these pins. So you just run the cleanup function. And basically, it just makes sure that random signals aren't still being passed back and forth once your program's done. For the most part, we're building kind of infinite loop programs, so I don't ever clean up after this, but this will kind of make more sense in a bit. Okay, so kind of recapping, you only really need to do 3 things. You just need to import the library, choose your board mode, and then set all of your input-output pins, and then you can just kind of do whatever you need to do. So, all right. Whoop. All right. Is this all making sense? I know it's kind of a lot to throw out in a short period of time, especially for 8:30 in the morning. All right. So the first project is just going to be playing with some LEDs. I call it the Hello World of Electronics. So everybody familiar with any of these 2 things? I hear some laughs. Okay, cool. Yeah, so we have kind of our Knight Rider in Kit, the talking car, and a Cylon from Battlestar Galactica. So we're going to have 8 LEDs that blink back and forth. So kind of like our Kit car or that. Really simple. So here's kind of what it looks like in a demo. Turns out live demos are hard when you have a whole other computer system you have to connect to, so we're just going to have videos for these. You can kind of see kind of a simple sort of back and forth motion. So for this, you need the Raspberry Pi and a power supply, breadboard. We're going to have 8 LEDs and resistors and jumper wires. So I'm going to talk about these parts here. Jumper wires are basically like pre-cut wires that are just really easy for breadboarding and prototyping things. So you don't have to really worry about soldering. They usually have male and female varieties if you have to plug into different types of components. LEDs, you've heard of these, I'm sure. Light emitting diodes. So basically, they're kind of like a small light bulb in a sense. But the diode part basically means that electricity only will go one direction. So if you plug the diode into a circuit, it prevents electricity from going the other way. And in this case, this diode glows when you apply electricity to it. But to help distinguish which direction you actually have to make the electricity flow, the longer one is the positive, and the shorter one is the negative. And they're called the anodes and cathodes. And then I always want to say always use a resistor. And the reason for that is if you just connect them straight up to a power source, they glow really bright and then kind of explode inside. So you get about 1 second of use before, which is really cool. You should do it at some point. But not always, obviously. So a resistor basically slows down that flow of electricity. So it resists the flow. So you really always need to use one of these with your circuits. So with them, the direction doesn't matter. You can just plug them in. They work either way. There's a bunch of band colors on them, and that tells you what measure of resistance they have. And like I said, without these, they kind of glow and then kind of don't work anymore. I like getting them in packs, so that way you don't even have to worry about like what kind of resistors you need. Like this one just comes with, I think I got like a kit of 100. That's like 100 LEDs and then 100 resistors, and I don't even have to mess with that. So I like that basically the whole point of this talk is taking the electrical engineering out of the electrical engineering, kind of making it like a lot more accessible to software developers. So I like that I don't have to do a bunch of weird physics calculations to figure out the kind of resistors I need. All right. So for wiring, it's going to be pretty simple in terms of like some of the more complicated things we're going to do a little later. So you're going to plug the ground rail into the ground on the Raspberry Pi, and then all of the LEDs are going to go into those Gpio pins. So the Gpio pins are going to be kind of your positive source into the LED, and then the LED is going to go back into ground. And then, like I said, you need to make sure those resistors are in there somewhere. So I think it's kind of easiest to Just kind of wire the GPIO to the LED to the resistor to the ground. You can do it the other way, like GPIO resistor LED. Either way, that kind of works for you. And remember that the gap in the middle doesn't connect, so I think it's easy to just plug the LED across that little gap in the middle. So our GPIOs will kind of become the power sources when we're kind of setting true and false to these output values. Yeah, so you can kind of see with the arrows sort of the flow of the electricity in this case. Okay, so the code's really easy. Like I said, import that GPIO library. Since we're kind of needing to slow things down to be sort of a rhythmic pace, we need to have some kind of pause functions, so we need to import the time library as well. It's kind of easier to use it with an array, so I just make an array of all those pin numbers, and that'll change depending on where you plug them into. And then I figured like 0.2 seconds seems like that perfect Cylon speed to like wait 0.2 seconds between each LED. So that's kind of the value I use there. So then we need to set the mode type that we're using. So like I said, I usually like the board type because it's easier to just see what pin number I'm using. And then for all of the pins, we need to set them all as outputs. So that's what we're doing. We're just sending output signals. So, so for each one of those pins in that array, we set it as an output. So here's where the actual brain of the program is, if you will. So line 17 is the infinite loop, so it just kind of keeps going because Cylons never die. Line 18 is the first 4 loops. We're going to go through every one of those pins, turn it on, wait for a second, and then turn it off. And once we've done that for all of the first 8 pins, we're going to go backward and do it that way. So we're going to do the range backward, which is what some of the negatives are. And then the -1 and the 0 is kind of weird in this case. So what happens is if you have 8 LEDs, you turn 1, 2, 3, 4, 5, 6, 7, 8. But when you go back, 8, 7, 6, 5, 4, 3, 2, 1. So you end up with this like double length on the ends. It looks like it's staying there longer. So really what we're doing is just going from like pin 1 through 7 and then 8 through 1 or 8 through 2. That's sort of essentially what we're doing. So now that you've seen the code, hopefully this makes a little bit more sense on kind of how this works. You can see sort of the different parts now that you know what they are. The LEDs that go across the gap, you can see the resistors are plugged in. Some of the wires come into the ground rail, things like that. All right, does this seem doable? I think I heard like 1 yes. It's because it's morning, right? Yeah. Hopefully this seems easy enough, and you know, maybe you can play with lights when you get home, maybe. So the next project I want to teach is some sensors. So you know, this is how computers kind of can interact with the world. In this case, we're going to start off with, there we go, an ultrasonic distance sensor. It's a fancy thing. I think it looks like ET or a robot or something. But basically, it sends out a signal we can't hear, finds out how long it takes to hit an object, and then bounce back. And because we know the speed of sound, we can calculate how long it takes to interact with something or find its distance. So the ultrasonic part basically means it's outside of our hearing range. So it's something like 40 kilohertz. And like I said, yeah, it just detects the time it takes to bounce against something. There's 4 pins on it. The first one's called VCC. That's basically our power. The second pin is a trigger. So when we send it a signal, it sends out the high-pitched sound. The other one is an echo. So it will actually like send a signal when it hears its noise back. And then the ground is obviously ground. I've seen some that are just one little doodad thing on it. In this case, one's a speaker and one's a transmitter. This one works on 5 volts. So you remember when I said like the Raspberry Pi works on 3.3 volts? So we're going to have to add a part in there to kind of help make it work. So don't cross voltages because bad things happen. I know I've fried so many boards over the years. In this case, you can use a 1 kilohertz resistor, and that's kind of one of those things you can buy in a kit. on the echo pin to kind of help bring down the voltage. So my little sample project here is this lovely thing. So the lights detect, show up how far something is. So as I bring an object up closer to it, the lights go off. And I think I set it up like each light was about 3 centimeters. So you could kind of measure out how close something is. So you could kind of use this for a variety of different things. What you would need for this is, of course, another Raspberry Pi, the breadboard again, an ultrasonic sensor. I'll talk a bit about these, but usually I can find like a kit of them for a couple bucks online. A few LEDs, a few of those resistors, and then that one special resistor we need, and then a whole bunch of wires. So we need to wire the Pi back up to the power on the breadboard. So hook up the ground and the power. We can wire both of the ground ones together. It might just be easier to be able to use both sides. So that's what the black wire on the side is there for. And then wire up all the LEDs just like you did before. They need to go in Gpio pins. And then the trigger pin needs to go to another Gpio. And then that echo pin needs to go to a resistor, which then goes to the Gpio. So basically, the wiring isn't that much harder or more difficult than before. It's just a few extra little wires and pieces to throw together, but generally pretty easy. The code's a little bit more complicated, but not too bad. So again, we need to import the time in the Gpio library. The time, obviously, because we need that, measure the time between objects. I set up pins for the ultrasonic trigger and the ultrasonic echo, as well as the LEDs in an array. And kind of same thing before. So we set up our board, set all of those pins to outputs, and then turn them all off for the moment. So that's what the Gpio low is for. Then we're going to make a function to read that distance. So this is a little hard to look at just here. I have lines in the GitHub repo for what everything does. But basically what we're going to do is we're going to set the mode to the board. We're going to set the trigger on, and then set the echo to be an input, which makes sense, and then turn the trigger back off again. So what ends up happening is we just really quickly turn it on and turn it back off. And we're going to wait a tiny little bit of a second, and that's just to make sure the sound is far enough away that it doesn't pick up its own sound. If you don't have that, you are always kind of tripping your own sensor. After that, we kind of flip the trigger again. Oh, this is actually where it happens. Flip it to true, wait like a tiny fraction of a second, flip it off, and then yeah. So basically the final while loop just says while that echo pin is still 0, just kind of wait, keep track of what time it is. And then eventually, once that echo flips, that while loop will quit and we'll know what time it is. So we'll know the time before and the time after. That's kind of what, yeah. Yeah, so the 0 is just to make sure it doesn't pick up its own sound, and then just where the input is 1 is where it does pick up its own sound. So the time passed is obviously the distance between the two times. 1700 is sort of a magic number, and that's the speed of sound converted to, I think, centimeters or something. So basically, the time passed times that will turn it into centimeters. That's the distance. And so this function can ultimately return the distance in centimeters. And then from there, we can use our main program, which basically loop forever, and then grab that distance from those ultrasonic pins. And then kind of use this for loop to say for every 3 centimeters, turn on an LED. And then after that, just turn off the other LEDs. So using that, it just can measure out the distance. So hopefully knowing that can kind of make this make a little bit more sense. So you can kind of imagine the sound waves bouncing against that little envelope thing I was using. And then as it's 6 centimeters, it turn on the first 2 lights and then not the next 4. All right, so that's one example of using a sensor. So I kind of want to make project 3 sort of an actual cool usable thing. You could actually build this and use it. So we're going to talk about push buttons and LCD screens next. So a push button is a button that you push. I hope that's easy. Makes sense. So basically, there's 4 pins. 2 of the pins are connected together. And then when you press the button, it connects the 2 pins across. So it's really easy. Those fit over the gap on the breadboard. And so you can wire it a certain way, and when you push the button, it connects like both sides. They're curved in a certain way. So I always have to look this up because I never remember. But if you can imagine, as they go across the gap, you end up having 2 switches. So 2 circuits can actually be ran from this. And pushing it down connects all 4 of them. And yeah, like I said, the curved pins, I sort of use the term hugging the breadboard. But yeah, they kind of go across that little gap. LCD screens, you've probably seen these in like some electronics and things like that. They're really easy because you can just send them ASCII characters and they show up on screen. So you can buy them in a variety of different row and column combinations. The smallest I usually see is like 1 by 16, and the larger I've seen is usually like 8 by 40. So they can come in a wide variety of different things. There's different types of them, but you'll want to look for one that says I2C or I2C, because that's the easy-to-use type. And basically, I2C is inter-integrated circuit. You don't need to know that. It's not important. It's a communication protocol for small electronic pieces like that. And your Raspberry Pi can talk over I2C conveniently, which is kind of nice. It's not enabled by default, so this is kind of one of those things you don't really need to know now. But if you run your configuration utility as root, go and enable I2C, reboot it, then you have access to those pins and can use them in that way. Wiring this is also pretty easy because, again, it's 4 pins. Your VCC is, of course, 5 volts again. Ground is ground. There's 2 pins. One's called SDA, which is your data, and one's SCL, which is your clock cycle, which, again, isn't really important. But there's 2 pins on that. Remember that chart with all the different things? You'll actually see 2 of those pins are labeled SDA and SCL. Those 2 pins have to go in those 2 particular connectors. I don't know why the video turned upside down. My computer, I normally show this on, the HDMI quit, so I had to convert everything over to LibreOffice on this computer. So something happened with the video. But this is kind of a Simon Says game. So let me have to, let's see if we can run that video again. So the idea is press a button to start, and then it shows 3 lights blink in a certain order, and you have to press the buttons in that order. And if you get it right, it says good job, and if you get it wrong, I think it just says you lose or something like that. But kind of a good example, and maybe you can play the game with your kids or something. Teach them the program too. So it's pretty simple as well. Raspberry Pi, breadboard, the usuals. You can get 3 push buttons. I usually found them in the kit. I think like 10 buttons for $3 or something like that. Some more LEDs and resistors. One of those LCD screens, which I think's like $2 or $4. And then some more jumper wires. So I use, on this diagram, different colored wires to show what components they're connected to, because you end up having a lot more wires connected to a lot more things. Basically, the ground goes to the black rail as usual. So the LEDs work just like they did in program 1. So the same kind of thing, plug them into the GPIOs. So plug one of the buttons into a ground, which is what the black wires are up there, and the other side to the GPIOs. So what we're going to do is end up detecting when you push the button, it's going to drop the voltage to a certain way, so we can use that as input. And then the cyan wires show the buttons connected. Not sure what happened there. So for the LCD screen, kind of like we said before, ground to ground, power to power. And then the orange wires up there are what specifically has to connect to the SDA and SCL on the Raspberry Pi, which is pins 3 and 5. OK, this one's a lot more complicated code, so I need to open this up over here. Oh, you're not going to work? OK. Okay, so this code's a lot longer, and I got tired of trying to put it on PowerPoint, so just open up the text editor. So like I said before, same imports. We got to import the Gpio and the time library. Since we're doing random stuff, blinking lights, we need to import the random library. And then I provide the I2C driver on my website too. It's out there on the internet, but I just kind of found it easier to just bundle it with everything else. Wire up some pins and LEDs. So keeping those in an array kind of makes it easier for debugging later, or just dealing with things. Just for simplicity's sake, I kind of made a function to turn LEDs on a little simpler, so it just turns on an output. If I want to do all 3 lights at the same time, I made another function for that. And then all 3 of them off, which is easy for like clearing out things, so just set all of them to false. Button press is a little bit more difficult, kind of in terms of how it works. So normally when we said we turn on a switch to provide power to something, when you push a button, what it does is sort of sucks away the electricity. And it's kind of weird to explain. But what we end up doing is we tell it to send out power, and then when we push the button, we kind of look for it to draw away the electricity, which is sort of what ends up happening on line 36 and 37. So we're kind of looking for that power to kind of go back false. So basically what we're doing in this function is kind of looping through all 3 buttons, looking for whichever one's pressed, and then returning whichever one of those 3 is. So 29 through 35 is kind of the ones that are looking for that. And for debugging, I just did a print statement on 33 that just say, yeah, that's the button I pushed. So I won't go over that too much more. The LCD screen is, whoop, come back. Pretty easy. So we have to load in the driver. And then for the moment, I turn the backlight off. So that's, you can make it like glow blue or green or whatever color your light is. For the beginning, I just keep it off. And then set our mode, set up all of our pins and our buttons and everything to their appropriate setup states. And then set the outputs on all the LEDs off. So it's kind of, all of that is setting up our game. Okay, so starting the game, why play Simon Says when you can play Sarah Says? So turn the light back on, make it show Sarah Says, print that on line 1, press the start on line 2, and then turn on all the LEDs, kind of like, hey, I'm ready to go. So then we just wait for any of the buttons to press. We don't care which one, so we just kind of run the function and don't even really collect its value. But once we get that, we can go ahead and turn off the lights, clear the screen, and clear off the backlight. So this little variable here, you can probably move it up for the sake of ease, but this is the number of times we're going to make it just blink different lights. If you want to make it really difficult and pester your friends, you can change it like 15. So for each one of those blinks, we're going to store a random number in an array. So it's just going to help us later when we're trying to figure it out. Flash those light patterns. So whichever random number we have, we're going to turn that light on, wait a moment, and then turn it off. And then do that many blinks number of times. And on our screen, we can turn it back on and say, repeat the pattern now. Or actually, we don't turn it back on. I think we just left it on. But yeah, so at this point, we say, hey, your turn. You got to play the game. So this is kind of the bulk of it. So for each one of those number of times we're going to play, so if we played 3 blinks, we're going to check 3 times. Get a button press. And then with all the lights off, yeah, because we don't want to leave one of them on. So every time they press a button, we're going to check if that button press matches that particular pattern. If they lose, show a sad face. And then change our winner flag to false, so that way we can break out of our loop. Otherwise, we just assume they got it right. We're going to just keep going until they finally get to the final pattern. And then if they're a winner, good job on the screen. And that's basically the end of the game. So sleep a few seconds, turn off the screen, turn off the backlight, and then clean up all of our things. So this is the one we don't have in an infinite loop. All right. A little bit more complicated, but still like fairly doable, right? So we're going to come back here. That is totally not the right side. Where's our game at? Slides are hard, especially at 9 in the morning. Where's the game? Yeah. There we go. Okay, so even though it's upside down, you can kind of see, blink a few lights. Now we're waiting for the button presses, make sure they match the patterns, show a good job on there. And then at that point, the screen would turn off. All right. So hopefully that's a game you could actually see yourself possibly doing. And one of the reasons I kind of showed off these projects was I was hoping to sort of get you in the mindset of, hey, these aren't really that hard to work with. They're a little daunting in the beginning, but they're actually really simple little components. And kind of simple in terms of how we think of programming, right? If we write little simple functions, larger programs don't get as difficult to write. So we can do the same thing with different hardware things. And so now I kind of want to use maybe the rest of our time to think through some future inspiration. So flap those little electronic wings of yours. So assorted ideas I've heard of, customized cookie maker machines. So some guy wanted to test out, does brown sugar work better than white sugar? Or, do cookies with an egg or without an egg taste better? Different things like that. So we put like all these ingredients in a machine and then would make like individual recipes for one little cookie. So this thing like dispensed out enough ingredients to make just one cookie. And so we'd try like a dozen literally different cookie recipes just with one cookie. That was kind of interesting. You could, one thing I've thought about doing was just put an LCD screen on my monitor and just having it show like when new emails show up, as sort of like a notification buzzer thing. You could take a remote control car and maybe like try to make it sort of drive itself around. So put in some sensors, make sure it doesn't hit a wall, but just drive around. Robots, of course. Who doesn't love robots, right? Home automation is kind of fun. So I've seen some kits where people started to build some libraries around our Raspberry Pis to attach different sensors and things so you can turn off and off lights in your home or control it like your thermostats, things like that. So that's kind of different things you could do with that. I thought it'd be cool to, as I leave a room, turn off the lights, but also maybe like close, your heater or air conditioner vents to kind of save some of your energy costs. I don't know, different ideas. Another thing I saw was somebody put a low-power Bluetooth sensor on their cat's collar. And so every time they would come up to a cat door, this device would read the Bluetooth, figure out it's their cat, and then unlock the door, which would prevent other animals from coming in. Different things like that. It sounds kind of fun. Somebody built a Christmas light color system, or controller system, and that's this thing. I forgot to plug in the sound. My fault. Oop. Oh, sorry. So I actually built this with a Raspberry Pi, connected it to some things that turned on and off different Christmas lights around his home. And then timed it out to the music to do different things like that. And Star Wars is totally appropriate for a superhero-themed conference, right? So the next one, so at South by Southwest a few years ago, Oreo came in and had a custom Oreo cookie machine, which is also really kind of cool. I'm actually going to show the video for that too. So basically on the front of the machine, they had a touch screen, and you could choose what colors and designs you wanted the inside of your Oreo to look like. And then they literally used a machine to make it, and you could watch it through a video. And they did it with a whole bunch of equipment. Part of it's done with the Raspberry Pi.
Color, we actually reverse it with negative pressure.
Now, I spotted a Raspberry Pi there. What's going on here?
Yeah, so all the electronics driving the whole machine are off this board down here with a Raspberry Pi and a Teensy. We also have a DeltaBot style platform for our X, Y, and Z control of the cookie. We put a custom cookie platform on that so we can hold on to the wafers while we move the cookie around underneath the print heads. So we have 16 print heads. This is the primary stepper motor that drives the carousel. You can see our admin UI that we built down here in C#. And that's how we kind of track what's going on with all the electronics and the motor status.
All in all, how long did this all take?
We built these prototypes in about 6 weeks. We started in the middle of January.
I'll go ahead and see if I
the
can
one
fast
we
forward
make-
to an example.
We already saw
but,
swirls, so
yeah.
we can kind of change our
There's a-
cookie design based on that. We can also change up some colors. Maybe I want a swirl. And then we can hit make cookie. And now you can see the machine is going to go and make that.
So thank you so much for showing us inside.
I was kind of hoping to.
See the mustache?
I know I've seen him actually like show where it was made, and I don't remember where that was at. But it's tethering
Comes out
off my
through-
phone, of course. But they do have a good part where they actually
Before
literally
they can
show
go into
like.
the robot.
I apparently lost that part.
Use the button from
Come on, show an example.
carousel that's got- that we
Yeah.
custom built.
So anyway, they attached a motor to it, so when they apply a motor, it rotates the thing. The little boxes above are pressure machines. They would pressurize the ink icing stuff, and so it would like squirt out, and then they'd use CNC motors, if you know the little machines that like drill out patterns, things like that. So they basically built a totally 3D printing icing machine before I think 3D printers really got super popular. So anyway, it's
Raspberry Pi there. What's going on here?
kind of fun, I
All
thought.
the electronic.
Another example that I forgot to include, a friend of mine took a Raspberry Pi and attached it to his garage door opener so he could text a code, and I think using something like Twilio would send the code to the Pi and then would send a signal to open the garage door opener. And somebody was telling me they really wanted to build like a beacon-based one, so they could build something into their car that would send a signal out automatically. So just when you drove up to the garage door, it would know it's the right car and open. So you can totally do different things like that with the Raspberry Pi. A lot of people ask, you know, this all is cool, but where would I get these parts? I think there's a Micro Center. Is it here or is it in Cleveland? I can't remember. Oh, there's here one. Cool. Yeah, you can go to Micro Center and get these. You can also get them online. They're usually more expensive on Amazon, so I say do not buy them from Amazon. Buy them straight from Element 14 or Adafruit. Power supplies, those you can pretty much get anywhere. Back on that tech specs sheet, towards the beginning of the talk, I tell what amperage you need for your power supply. So depending on which one you buy, you need different amperages. So you need that value or higher. So like if it needs 2 amps, you just need like 2 or higher amps for your power supply. Breadboards are kind of everywhere. If you can find an electronics store or Micro Center, you can get them on Amazon pretty cheap too. Jumpers, kind of the same things. Sensors, you can buy them individually. You can also buy cool little like just tinkering kits. So they'll include like 10 different sensors. I bought one kit once. It just had like a humidity sensor, temperature sensor. I'll never remember what else. Like photo sensors, they detect like how much light is coming into it. You can just get different kits like that online too if you're looking for just kind of random inspiration. So some final thoughts, I guess. We always think that dev projects are, you know, they take a while to debug, and sometimes we struggle to make sure they get going. They always seem to take longer to debug than we think they will. Hardware projects usually are going to take even longer, because part of the problem is you don't always expect the hardware to go wrong, right? Sometimes sensors can go bad, sometimes other things happen. So account some time for debugging your code, but also realizing like if you're sure your code is perfect, it might be. Your hardware sensor might went bad. On one of the robot teams I was in college, we had this problem where some of our sensors would sometimes work, and then they sometimes wouldn't work, and then they'd sometimes work again, and then don't work again. And usually things don't break and then fix themselves. So we were having trouble trying to figure out what was happening with that. We found out some of the materials we were building the robot out of was conductive, and the sensors were touching it. And so we ended up like sometimes shorting out these sensors, and we didn't know why. So I got some extra time for that. Like I said, hardware can sometimes fail sort of randomly. And always, if you're building a project and you have some questions, you're welcome to contact me. So kind of to wrap it all up, you know, Raspberry Pi is kind of a basic PC, but it also has those GPIO pins. We can do really cool projects with those. Hopefully you've seen a bunch of different sample projects, maybe to inspire some ideas of things you can do around your house, or maybe things to work on with your kids if you have them, or just different things you could do at work maybe. Now that I think about it, some guy was telling me he built one that was attached to a sound system so that it detected somebody's Wi-Fi on their phone when they walked in and would know who it was that was connecting and then would play their entrance music. So you could choose like a theme song that every time you walked into the office, it would play for you. You know, maybe there's valid work projects you could do with this too. But hopefully in the end, I've just kind of hoped you're sort of inspired to maybe be creative and maybe put that Raspberry Pi that's in your junk drawer somewhere to good use. So thank you for coming. My name is Sarah Withee. Everything's online at that website. All the code, all the videos, all the diagrams, literally everything. I would love to hear stories of what you build. If you're inspired, come find me in the hallway. We can talk about it. You're welcome to just reach out on email or Twitter, anywhere, things like that. Yeah, just keep in touch. I'd love to hear from you. Thanks.